Hello everyone. Welcome to episode 3 of the Transistor tutorial series, BJT Biasing and Small Signal Model. In the previous episode, we went over the basic structure of BJTs, their operating modes, and the BJT large signal model. In today's video, we will be discussing the concepts of biasing and small signal analysis. Then we will go on to apply these concepts to the problem of biasing and small signal analysis for a diode, and then apply these concepts to the BJT with the hybrid pi small signal model. Finally, we'll make a slight adjustment to the model to make it more accurate under certain conditions with the introduction of the early effect. So, small signal analysis. In order to discuss the usefulness of small signal analysis, we have to first talk about linearity. A rough informal explanation for linearity of a circuit with a single input and single output is when the change in its output signal is equal to the change in its input signal multiplied by a constant. In the equation below, the output signal is x out, the input signal is x in, and the constant, also called the gain, is k. We can see that the absolute value of the input signal does not matter in this case, only changes in the input signal, denoted by the delta. This is one of the benefits of linearity, that the gain of the circuit does not depend on the signal level, that it is the same for all input signal levels. In contrast to this equation, we look at the large signal BJT current voltage equation from the previous episode. We see that the input signal is given as V in, and the output signal is I out. However, this circuit is nonlinear. The absolute value of V in is a consideration. We cannot just use changes in V in, because, for example, a change in voltage of plus or minus 5 millivolts around a V in voltage of 0.5 volts will produce a much lower output current change than a change in voltage of plus or minus 5 millivolts around a V in voltage of 1.5 volts. So the BJT large signal model is very nonlinear. So why do we care about linearity? Linearity is an extremely important property for most analog circuits. One of the main reasons, especially for radio frequencies, is that linear circuits don't generate new frequencies apart from those at their inputs. What this means is that if I have an input signal that only has frequencies from, say, 100 Hz to 1 kHz, and I pass it through a linear amplifier or filter, then the output signal of that amplifier will have at most frequencies from 100 Hz to 1 kHz. A linear filter circuit can suppress some of those frequencies, but it cannot create new frequencies outside of the ones from the input signal. This is important because it means you don't need to make your circuitry faster or slower than your input signal to make the output signal correct. And for signals that need to remain confined to certain frequency ranges, such as with radios, so long as the input signal is confined to that frequency band, the output signal will be as well. Another important reason is that error sources like noise and offsets tend to have a much simpler effect on the output in a linear system and are much easier to compensate for. For example, if you have a signal that's at a small frequency band around 10 kHz and unwanted noise that's at a small band around 60 Hz, a linear amplifier circuit will amplify both signals separately in frequency space so that the 60 Hz signal could be easily suppressed by simply filtering out all 60 Hz content on the output. By contrast, in a nonlinear circuit, the 60 Hz waveform could affect the gain at 10 kHz, thereby distorting it in such a way that it is difficult to correct. A third reason for precision circuitry is that a linear circuit can be much more easily calibrated. But the most important reason to avoid nonlinearities is that the principle of superposition that we so often use to split circuits into simpler pieces, then recombine them later after solving each piece, cannot be applied to nonlinear circuits. This makes nonlinear analysis even more difficult. There are other reasons, and an in-depth discussion of why linearity is so important is beyond the scope of this video. But suffice it to say, linearity is a very desirable attribute in most analog circuits. So now we need to see if there's a way to make our nonlinear circuit somehow linear. The way we do this is through small signal analysis. In small signal analysis, we make use of the fact that nonlinear circuits are approximately linear if the input signal is kept small enough. To facilitate this, a large DC signal is applied to the circuit to get the gain into the right range. Then the small signal is applied on top of that large signal. This large DC signal is called the bias. There are several ways this bias can be applied, and the method by which bias and small signal are applied is application specific and also depends upon whether or not the circuit is made up of discrete transistors or if it is part of an integrated circuit. Sometimes additional circuitry is added to further linearize the circuit. We will discuss some of these methods in later videos. For the most part, though, most circuit analysis occurs in the small signal domain, and signals are kept small enough and gains high enough for this to work out well. Any small remaining nonlinearities are generally ignored in the analysis and only examined and mitigated after the circuit is simulated or tested. Now that we have this rough definition, let's see how to apply this method to a simple diode circuit. While a diode does not provide amplification, it is simpler than a transistor and similarly nonlinear, so it is therefore easier to introduce the process of small signal analysis with a diode. Here we have a diode D1 in series with a resistor R1 with 3 nodes of this circuit labeled A, B, and C. So first we need to know what the current voltage relationship of a diode is. So here we have the Shockley diode equation for an ideality factor of 1. The parameters in this equation are the thermal voltage, reverse bias saturation current, diode voltage, and diode current. Thermal voltage is about 26 millivolts at room temperature. We're going to generally assume the diode is conducting enough current to be considered on, which will result in the diode current being much higher than the reverse bias saturation current. So this produces a simplification where we get rid of the -1 in the diode equation. This simplification is usually very accurate and will be more important in a moment. Now to simplify the circuit even more, let's ground node C. So we have a sort of divider between A and B, with the resistor on the top of the divider and the diode on the bottom. Now we need to apply a sort of biasing signal and an input signal. So let's add a few more components to this circuit. Here I've added an input AC voltage source Vin, a DC bias voltage source Vbias, 2 capacitors, one in between Vin and the divider circuit, and one in between the divider circuit and the newly defined output voltage node Vout. Now let's set Vin to be a signal that only contains frequencies that are above a certain frequency, so we can say that Vin is a high enough frequency such that L1 is effectively an open circuit, and both C1 and C2 are effectively short circuits, at any and all frequencies that the Vin signal operates at. This effectively cuts off the I bias voltage and shorts Vin and Vout to the top and middle of the divider respectively. Conversely, V-bias is a DC voltage, so L1 is effectively a short circuit, and the 2 capacitors are effectively open circuits. This effectively cuts off the input and output nodes from the circuit and shorts V-bias to the top of the divider at the resistor. So we can think of this circuit as 2 separate circuits, one for DC signals primarily involving V-bias, and one for AC signals primarily involving Vin. Like this. Now we have to make some assumptions in order for us to recombine these circuits later, since, as mentioned previously, superposition does not apply to nonlinear circuits. First we set V-bias to a high enough value, and Vin to a low enough amplitude, such that ID bias is much greater than ID SM. And thus the total diode current ID is approximately equal to ID bias. The key to small signal analysis is to apply this approximation only in some places where it helps linearize the circuit. The core point of all this is to divide the circuit into a large signal portion and a small signal portion. The upper circuit performs the biasing. Biasing in this context is providing a large signal to set the approximate location of the voltage and current on the exponential diode curve. For example, V-bias might be set up so that the diode current is approximately 25 mA as shown in this plot of diode current versus diode voltage. Then, Vin from the lower circuit applies small voltage and current fluctuations to the diode that we can assume to be approximately proportional to the slope of that point on the curve. Since our capacitors and inductor block the bias voltage from appearing on Vout, then Vout only consists of these small perturbations produced by the lower circuit, which we call our small signal circuit. So long as we keep the small signal voltages and currents small compared with the bias currents, we can generally assume that Vin doesn't cause the diode voltage and current to really move around enough on the diode curve for that slope to change significantly, which allows us to assume that slope is a constant for all Vin values. So we can think of IDSM and VDSM as small changes in the total ID and VD values. So we define these two equations, which we will use in a moment. To calculate the bias current, we assume the diode drop is about 0.7 volts, and then calculate the current from that. This varies depending upon the diode and the approximate desired bias current, as well as the desired accuracy. So ID is approximately V bias minus 0.7 volts divided by R1. So now we focus on the small signal circuit. As we said, if Vin is a small enough signal, we can assume that the current voltage relationship of the diode due to this additional small signal is approximately linear, and a linear current voltage relationship is just an impedance. So we get to replace the diode here with an AC impedance ZD1. And by definition of AC impedance and impedance, 1 over ZD1 is equal to IDSM over VDSM, which is also equal to delta ID over delta VD as per the equations at the bottom of the slide. For small enough delta ID and delta VD, we can approximate this admittance as the derivative of ID with respect to VD. This derivative is the key to the small signal model. Taking this derivative of the Shockley diode equation, at first it doesn't look like we've improved the situation by much, as there's still an exponential in this equation. But we see that this portion of the equation is equal to ID, which is where we use our approximation that ID is approximately equal to ID bias, because ID bias is much larger than IDSM. And so we can approximate the derivative as equal to ID bias over VT. Noting that since there's no frequency dependency in this expression for 1 over ZD1, ZD1 can be expressed as an AC resistance rather than an impedance. Note that I've used a lowercase r here. This is because the convention for small signal analysis is to use lowercase letters for small signal parameters like this small signal resistance. So we get RD1 equal to the thermal voltage VT over ID bias. And this is our resulting small signal circuit for the diode. Now, instead of a highly nonlinear device that we don't really know how to deal with, we can now use simple circuit analysis with the standard set of linear components, resistors, capacitors, inductors, voltage sources, and current sources to produce useful results. This particular circuit works as an AC electrically controlled variable resistive divider. V-bias can be changed to make the resistive divider ratio of the small signal portion of the circuit different. Larger V-bias will make RD1 smaller and thus make the gain of the circuit less. And conversely, smaller V-bias will make RD1 larger and make the gain of this circuit higher, though the gain will always be less than 1. A circuit similar to this kind of circuit is used in RF electronics as an electronically variable attenuator to great effect. So we've shown that we can use the nonlinear large signal model to get approximate voltages and currents to get the circuit in an approximate region of the nonlinear current-voltage relation, then confine our application signals to be small enough that they can be linearized around that region. You may note that I haven't given any specifics as to how small the small signals need to be. The truth is that it's very application specific, but a small signal current, about a factor of 10 to 100 smaller than the bias current, is a starting point rule of thumb. However, some circuits care less about nonlinearity, and some circuits need to be very linear. It all depends on the application, including whether there are any additional linearizing aspects like negative feedback that minimize the effects of the nonlinearity. Now that we've introduced the concept of biasing and small signal analysis, let's apply it to our bipolar junction transistor. With the diode, the main parameter that needed to be set by the biasing circuitry was its current. Similarly, the main biasing parameter for the BJT is its collector current. There are various ways this current can be established and the biasing circuit separated from the application signals. Perhaps the most traditional introductory method is setting up the circuit this way. With an input voltage on the base, output from the collector, with capacitive coupling in series with the input and the output, as well as a resistive divider on the base, with an emitter resistor in parallel with an emitter capacitor to ground. This kind of circuit configuration is called a common emitter circuit with a kind of emitter degeneration, which just means there's a resistor on the emitter to ground. The idea here is that C in, C out, and CE are all open circuits for the DC biasing, and are short circuits for any and all of the V-in signal frequencies. So let's split the circuit into the DC large signal portion and the AC small signal portion. Here we have the DC biasing circuit on the left and the AC small signal circuit on the right. You'll note that in the small signal circuit, all the VCCs have become grounds. This is because the small signal circuit only deals in AC voltages and currents, and since VCC does not change, it is functionally equivalent to ground in an AC model. Let's focus first on the biasing circuit and describe how to set it up for a specific collector current. Then we'll move back to the small signal circuit in a bit. So with the large signal model, from what we discussed in the last video, it seems like we're supposed to use the exponential to calculate collector current. Using the exponential is difficult to do because the reverse bias saturation current of discrete transistors varies widely and is not usually well documented. However, the addition of this emitter resistor actually helps us avoid having to use the exponential at all. We can just assume the base emitter voltage is around 0.6 volts or 0.7 volts, and then the remaining voltage drop across the emitter resistor defines the collector current. I'll explain how to do that in a moment. In most cases, the exact collector current is not that important. We only need to get it roughly correct, and so this method will work just fine, and the actual value can be tweaked in simulation or test later if necessary. The process of designing a transistor amplifier circuit is a very iterative process, as each parameter has trade-offs. Additionally, as pretty much each parameter impacts all the other ones, they have to kind of be designed in parallel rather than one at a time. For today, though, we won't be going into the trade-offs of each parameter. We're just going to focus on designing a specific IC bias. As we progress through this tutorial series, we'll discuss the various trade-offs of each parameter further. So, we choose a target IC bias, RC and RE, keeping the following relations in mind. The DC collector voltage, VC bias, is equal to VCC minus RC times IC bias, and the DC emitter voltage, VE bias, is approximately equal to RE times IC bias, since IC and IE are about the same in a transistor when we assume that beta is large. So increasing the collector current increases the voltage drop across these two resistors and narrows the voltage between the collector and emitter. So in order to keep the system in the forward active region, keep in mind that you need to keep the collector voltage above the base and the base voltage above the emitter. So with our target IC bias, we now note the following equation for IC bias. This is why the emitter resistor is helpful. Small changes in the 0.7 volt VBE drop have less of an impact on the bias current by having VB bias and RE. The higher VB bias is, the less of an impact the 0.7 volt drop has on the collector current. So if you increase VB bias and RE together, you can keep the collector current the same while reducing the effect of the 0.7 volt VBE drop. So now we need to set VB bias, which is given by this equation. Keeping RB1 and RB2 large will minimize the effect they have on the small signal model. In the diode example, I used an inductor to block all AC signals, but that was more to illustrate the point. In reality, using an inductor to block the biasing resistors won't work very well except for very high frequency and narrow-band small signal circuits. However, we can't just make RB1 and RB2 really high resistances, as some consideration has to be made for the base current due to finite beta. The best way to deal with this is to get a range for beta with your target collector current, then set the resistors values so that the resulting base current doesn't affect the voltage at the base all that much, then slightly increase the size of RB2 to compensate for the base current. Again, while it seems like we just decided upon IC bias, VB bias, RC, and RE all at the same time, this is an iterative process and often informed by previous designs. Designing an optimal bias point for the application is one of the complex aspects of analog circuit design, so unfortunately, there isn't a very straightforward recipe for doing that. It's important at this point to note that there are many kinds of biasing circuits. This one is a common introductory biasing circuit that works okay for discrete transistor circuits. However, this kind of biasing circuit is almost never used for integrated circuits. Integrated circuits use more complex and generally more effective biasing circuits using current mirrors and active loads, which are beyond the scope of this video. There are many different ways to bias a transistor circuit, and you can probably come up with many different ways that may be more effective than this circuit depending upon the application and desired cost. This circuit merely serves as an introductory bias circuit, though for many situations it is more than adequate. Now that we've figured out how to set up our collector biasing current, let's move on to the small signal model for the bipolar junction transistor. So how do we turn this nonlinear circuit that we don't really know how to deal with to a linear circuit that can be analyzed with the familiar circuit elements of resistor, capacitor, inductor, voltage, and current sources? I've labeled the collector and base currents as IC and IB respectively. Note that I've labeled them as lowercase letters with lowercase subscripts. This is a convention in small signal analysis where small signal parameters are denoted by lowercase letters with lowercase subscripts. DC bias quantities are denoted by uppercase letters with uppercase subscripts. I sort of did this with the biasing circuit earlier, though I changed the name of the subscript for clarity.
Finally, the total value of a parameter is denoted by a lowercase letter with an uppercase subscript.
Additionally, oftentimes values that have equal DC and small signal quantities, like these three resistors, are just left with the DC convention of uppercase letter and uppercase subscript. Now recall from the diode example that we utilized the idea of a large bias current, meaning that the small signal currents do not affect where we are on the exponential diode curve. Since the Shockley ideal diode equation we used on the diode earlier has a similar format as the equation for the collector current versus VBE in our large signal model, we can apply the same approximation, assuming IC is much greater than IS. So we recall that when the voltages satisfy the requirements of the forward active region, the transistor can be thought of as a voltage-controlled current source controlled by this equation, which is represented by this diamond-shaped current source called a dependent current source. We see that on the top is the collector, which is connected to RC, and on the bottom is the emitter. I haven't drawn in the base yet. We'll get to that in a moment. First, let's focus on the collector current. What is the small signal value of the collector current? As before with the diode, we need to take the derivative of IC with respect to VBE to get the slope of the voltage-current relation and the bias point. And similar to the diode, it is equal to the collector bias current divided by the thermal voltage. So the small signal collector current is just the small signal VBE times this derivative. So IC is equal to VBE times IC bias over VT. We call this parameter, IC bias over VT, the transconductance of the transistor, denoted by GM. We still need to calculate the small signal parameter that handles the base current and base emitter voltage relation. So we have the expression for small signal collector current, which is VBE times GM. We know from our definition of beta that the base current is just this value divided by beta. Thus, base current is equal to VBE times GM over beta. If we divide both sides of this equation by VBE, we get IB over VBE equal to GM over beta. Recalling Ohm's law, we see that a current divided by a voltage is a conductance, or an inverse resistance. So all we need to do is invert both sides, and we get the resistance parameter equal to beta over GM, which is equal to beta times VT over IC bias. This expression is defined as the resistance parameter R pi, and it goes here in our small signal model. I've also added the input voltage, source resistance, and biasing resistors back in. It's worth mentioning that we define another resistor, Rm, as the inverse of the transconductance. Though it does not appear in this small signal model, sometimes it appears in other models. So here's our small signal model for the circuit we set up. I constructed a real circuit around this transistor just to connect it to a real-world circuit. However, now that we've constructed the small signal model, let's strip away the application-specific components and just look at the core model. Here we have R pi, IC equal to GM VBE, and our three terminals. You'll note I've eliminated Vin and Vout because the location of Vin and Vout, or In and Iout as the case may be, is dependent upon the application. So we can see that the transconductance, GM, can be increased with the bias current, and therefore effectively increase the sensitivity of this circuit to the base emitter voltage. In many applications, this allows us to control the gain of the circuit. At the same time, increasing the bias current also reduces R pi, making the input impedance from the base's perspective lower, which makes it harder to drive the base. This is one of the trade-offs of collector current. However, there is one more small signal parameter we need to define, and it's actually something we left out of the large signal model. It's called the Early effect, named after the person who discovered it, James M. Early. It is a change in collector current and beta due to the collector emitter voltage, meaning that as the collector emitter voltage changes, the collector current changes even with a fixed base emitter voltage. So, briefly looking back at our large signal model, here are the two central equations. We've incorporated the assumption that IC is much larger than IS here. And here are the modifications from the Early effect. This parameter, VA, is called the early voltage, and its value is dependent upon the transistor you are using. The physical cause of the Early effect is changes in the depletion region of the base collector PN junction due to changes in the collector emitter voltage, with a fixed base emitter voltage, causing an effective decrease in the width of the base region. This decrease in the width of the base region has the effect of increasing the value of beta. This is, however, a relatively small effect, as VA tends to be on the order of around 100 volts for discrete transistors like the 2N3904. And so you only get a significant effect if VCE is large, which can't be very large without destroying the transistor. So the effect is generally ignored in the large signal model when calculating bias currents, since there are already a lot of approximations and uncertainties. But it produces a much more important effect in the small signal model. Since the Early effect describes a small change in the collector current due to change in VCE, you might imagine that this implies that we need to add a small signal resistance between the collector and the emitter. So how do we calculate this small signal resistance? As before, we apply a derivative to the collector current expression, but this time it's the derivative of collector current with respect to VCE, not VBE. So here we have the equation for IC. Now we take the derivative of IC with respect to VCE. This is a relatively straightforward derivative since there was no VCE in the exponential. Next, we recall in our previous approximations we assumed the bias current, IC bias, is approximately equal to IC, which produces this adjusted equation due to the Early effect. However, we note that this full expression does not appear in the derivative above, so we need to do some rearranging before substituting it in. Here we have the exponential times IS is approximately equal to the bias current times VA over VA plus VCE. Substituting in this expression for the exponential in the derivative above, we get this equation. Canceling out the VA terms and inverting it so we get the value in resistance rather than conductance terms, we have a small signal resistance RO that is approximately equal to VA plus VCE over IC bias. Usually this parameter is approximated to just VA over IC bias, as VCE is often significantly less than VA, though sometimes it's worth using the more accurate version for RO. The resistance, RO, is, as expected, a resistor in between the emitter and collector. It looks innocent enough in this schematic, but in practice RO is the most annoying of the low-frequency small signal elements when trying to analyze a circuit, and so we often do our best to come up with ways to make it insignificant so we can ignore it. Additionally, it's useful to note that RO becomes smaller and thus more prominent the higher the collector bias current is, and so it represents another trade-off of the bias current. So here we have our complete model, what is called the low-frequency hybrid pi small signal model. This model allows us to build up circuits and perform the familiar linear analysis on them, so long as we keep the signal small with respect to the biasing current. A few final notes about the purpose of small signal analysis by hand. These days, computers are so much more powerful than they were in the early days of analog design that one might wonder what the point of learning all this is. Wouldn't it be simpler and more accurate to just simulate the circuit using a computer? This is true. A program called SPICE was developed at UC Berkeley for this very purpose. And computers running SPICE will always simulate circuits far more accurately than these so-called hand calculations. However, hand calculations provide much greater insight on how to optimize and improve circuits during the design phase. Simulations will show with great accuracy how they will behave, but provide very little insight as to which circuit parameters contribute to the desirable aspects of that behavior and which contribute to the undesirable aspects of that behavior. Thus, it becomes very difficult to determine how to set the resistances, bias currents, etc. to optimize a circuit for a given set of application requirements using just simulation data. Hand calculations, by contrast, provide a rougher picture of the behavior, but much greater insight on what controllable aspects of the circuit contribute to that behavior. And so we can take steps to improve the circuit through the insights produced by the hand calculations. While we call these calculations hand calculations, there is software that can perform symbolic manipulation, like Mathematica, that can do most of the algebraic manipulation. But the hand part is still setting up the circuit and figuring out the initial set of equations. Even though symbolic algebra programs open the doors to even more complex circuits, it's important not to make the equations too complicated. Good approximations, and ignoring insignificant parameters, keep the hand calculations simple and insightful. Incorporating too many parasitics, or trying to optimize so far that parasitics start to dominate too many terms, tend to create complex transfer functions with too many poles and zeros or too many mathematical parameters, and the whole model stops providing insight to the designer. The designer must strike a balance between too little accuracy and too little insight. And once an initial cut is designed, simulating and testing the design is crucial, but only after the hand calculations. Then after simulation, the design is refined and the process begins again. That concludes this episode of my transistor tutorial series. In the next video, we will be introducing the common emitter circuit, which we used in the first episode, except this time we'll be going into significantly more detail and exploring the small signal equivalent circuit for it. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.